All right, so in lecture 2, we started moving a little bit more deeply into our acid-base chemistry, started talking about buffers, and we're going to see buffers in both lab and lecture here, kind of thinking about Henderson-Hasselbalch equation, and then also spending some more time thinking about the blood buffering system. A little bit of a sidetrack here, talking about too how we view and think about plots and charts that we might see. So again, I'm going to go through a little bit more quickly. We spent a little bit of time talking about a bunch of carbonyl containing functional groups. So remember, carbonyl really just represents that C double bonded to O. If we've got R C double bonded to O, we can call this an acyl group. If it's a methyl group that's there, we're going to call it an acetyl group. Okay, so what you are in terms of a functional group depends on what's next door. You have a hydrogen, you're an aldehyde. You have another carbon atom, you're a ketone. You have an OR group, which we call an alkoxy group. That's going to be an ester. And if you swap out that oxygen for a sulfur, we call that a thioester. So thinking about where we find these and why they're important. So again, both aldehydes and ketones are very important because when we're talking about carbohydrates, the carbon at number 1 or the carbon at number 2 in all carbohydrates is going to be a carbonyl. And so again, if the carbon is at carbon 1, that means the functional group we'll have there is an aldehyde. We're going to call these sugars aldose sugar, and the classic aldose sugar that we're going to spend some time studying is glucose. If that carbonyl is at the C2 position, that's going to make it a ketone, so we call those sugars ketose sugars. Classic ketose sugar that we'll study is fructose. Ester functional groups, the main place that we're going to see an ester functional group is if you take fatty acids, which have a carboxylic acid functional group, you hook them onto a glycerol backbone, and glycerol is a polyalcohol, so we've got OH groups. This is called Fischer esterification. A carboxylic acid plus an alcohol gives us an ester. So what we see is we're going to see kind of, I'm going to show with my fingers here, this is going to be 3 fatty acids that are hooked on a glycerol backbone. So what links my fingers to my knuckles is an ester functional group. Okay, so we call these triglycerides. So triglycerides are going to be a really important ester-containing molecule that we'll study. Again, as you swap out that oxygen for a sulfur, one of the things that happens is all of a sudden this bond becomes a high energy bond. We can actually store energy within that high energy bond. And if we think about a molecule that's really important for having a thioester, it's the molecule acetyl-CoA. So pyruvate is converted into acetyl-CoA by an enzyme called pyruvate dehydrogenase, and then acetyl-CoA is what goes into the citric acid cycle. So if we think about what the structure of CoA looks like, this is a vitamin B derivative, and so what we're going to see here is we've got a thiol functional group at the end, and what we're going to see here is that when we attach a 2-carbon acetyl group to it, that's how we get acetyl-CoA. All right, so that was our functional groups for today. We spent a lot of time today talking about buffers, and I used a lot of analogies to have you imagine that buffers are really like your army that helps prevent change in pH. So just a little kind of introduction here, stuff that we talked about that really wasn't part of the notes. Imagine I've got a container of really strong hydrochloric acid and really strong sodium hydroxide. Strong acid, strong base. If I take just pure water and I just drip a little bit of either one of those into that water, what's going to happen is I'm going to drastically change H plus concentration if I've added HCl, or I'll change OH minus concentration if I've added this sodium hydroxide. Regardless, if I have pure water, what happens is I have a drastic change in H plus or OH minus concentration, and that results in a drastic change in pH. So now imagine that I've got my beaker here, and rather than having pure water, I have a solution that contains a weak acid and its own conjugate base. I've created a buffer when I make that solution. So why this is important is I now have 2 molecules in there that can act as soldiers and defend against attack by either acid or base. All right, so envision this. If I've got a weak acid and its conjugate base, the weak acid can react with any of the sodium hydroxide I might add. So if I add that sodium hydroxide, that hydroxide will react with my weak acid and gets neutralized. Okay, so we're not going to have that dramatic change in hydroxide concentration. Flip side, if I've got my conjugate base in solution, and I add some of my hydrochloric acid, that H plus that comes in is going to then react with my conjugate base, and it's going to neutralize it. So again, imagine your buffer being really an army of acid and base destroyers. Okay, so that's what we're going to have here. So we're going to talk a lot more about buffers in lab, and we're going to do the heavy lifting in terms of calculations in lab. I do have 2 homework problems that are going to ask you to understand how to do this, but for the most part, you'll learn how to do that in lab, but I have a couple of homework problems here. So what I have in this table right here is just a bunch of different acids, and all of these acids have different pKa values. So different acids are going to have different pKa values. That's a property of that molecule. So again, this is just another one of these ways to think about what happens when you add either a strong base or a strong acid to a solution that has a buffer. So I want you to imagine these little sort of pillars that we have here. They represent containers, if you will, that contain, in this case, our weak acid, which is going to be the molecule that will react with base if it's added. So this is kind of our defender against bases. This is our defender against acids. And right now, when we start out, we've got equal amounts of both of them. And we've got a relatively large army of both of them. So again, what happens is if we're attacked by acid, it's going to deplete a little bit of our base army. And so that one goes down, and because we make HF, we actually increase a little bit of our HF army. The opposite is true over here. If we have an attack by an acid, a base, our base is going to attack our weak acid here. It's going to deplete some of that army, and it's going to then convert some of that army into the base, the weak base army. So what sort of happens here, and this was a great question that came up in class today, well, how long can this happen? How long can you sort of skew this before it becomes problematic? And truthfully, if the balance between your acid and your base components of your army gets more than a 10-to-1 ratio, you've lost what we call buffering capacity. So we'll get to that in just a minute here. Okay, so the Henderson-Hasselbalch equation, we've introduced that. We're going to use this a lot. We'll use it in our case study on Friday. The Henderson-Hasselbalch equation is really important because it allows us to think about the pH as a function of a property of a molecule, and then the concentrations that we'd have of that molecule as its weak acid and conjugate base form. So when we think about buffer capacity, when are we going to have the best army? What's going to be the best situation for us to be able to buffer our solution? Well, we'd like to have relatively equal sizes of our army, okay? And how we have relatively equal sizes of our army is we can match our desired pH to our pKa. This is actually your second homework question. This is not overly difficult. All you do is look at a table like this. If you want to have a pH buffer that's 4.75, let's say, I just need to pick an acid system whose pKa is closest to that. It's as simple as that. But let's look at the math of understanding why. If I wanted to have a buffer that was pH 7.5 or 4.75 and I chose acetic acid, the pKa of acetic acid is 4.76. So again, there's very little difference between here. Let's imagine that they were exactly the same. Essentially what that would be is 0 equals the log of whatever that ratio is. That ratio is going to be 1. That tells me that I will have equal amounts of both kinds of my army when I choose an acid whose pKa is equal to the pH I want to be at. If you need to, replay that last 15 seconds so you can hear that again. But if I want to have an equal army, relatively the same amount of both of these, I want to choose a buffer or an acid whose pKa is pretty much equal to the pH I want to be at. Okay? A second piece to thinking about buffering capacity is that we want our army to be relatively large. Coming back to this picture, if our army was only this big, it wouldn't take very much before we'd have an attack by either acid or base, and we'd deplete that kind of soldier. So in that case, we want to have the concentration of our conjugate base and our weak acid be a relatively large number. For right now, we're going to say from a laboratory standpoint, you want to have at least 10 millimolar concentration. If you're less than that, you have a pretty small army. So Henderson-Hasselbalch equation, we're going to use this in a variety of different ways. Okay, we're going to use it in our aspirin overdose case study on Friday as a way to calculate pH, or to think about, this is really a 4-variable equation, right? pKa is a constant. We're generally not going to be solving for pKa, but we might want to be solving for what the pH of a solution is when we know these two pieces. Or if we know pH and maybe we know something else, maybe this guy's the unknown. So we'll do that in our case study on Friday. But from a laboratory standpoint, we might know the pH we want to be at. We're going to choose the acid to have a pKa that matches. And then we need to figure out what are the concentrations of these two guys that we need to have in order to make that buffer. And so we need to have, like with our lab math calculations, we need to have practical go in the lab, weigh out this amount of stuff sort of calculations. So homework problems 3 and 4 are going to address this, as well as 2 larger problems that we'll deal with in lab. All right, the rest of our time was spent on 2 main slides here. The first slide was just running us through how do we think about looking at figures and figures of graphical data. So the first thing that I told you needed to do when you had something that was graphical is look at the axes. If there's not axes, they're not effectively conveying whatever it is the information that they want to convey. So for this problem, we're asking about how pH is dependent on the concentration of hydrogen ions that are dissociated per molecule. We also talked about how I really don't like this phrasing because it sort of makes it sound like you could have 0.4 protons dissociated from a molecule. Remember, protonation and deprotonation is a binary event. It's either on or it's off, right? So we don't have a molecule that has half of a proton. What you can have is you can have half of the population that has lost its proton. And that's a really important distinction that I want to make sure to introduce early, and we'll sprinkle that in throughout the rest of the course. So again, the first thing to do is read the axes so we understand what we're visualizing on our graph. And then importantly, we're going to do this several times throughout the course here. We're going to think about vertical lines and horizontal lines and what the information is telling us as we see both of these, okay? So anytime you draw a vertical or a horizontal line, what you're really saying is, I want to hold this variable constant and I want to see how the other one changes, okay? So let's take first horizontal lines. If we're holding a horizontal line, that means we're keeping pH constant, okay? So if we're keeping pH constant, we're asking, how does this percent dissociation change as a function of these 3 different graphs that we have here, 3 different lines. So when we're going to draw a horizontal line, we're going to ask, where do we intersect each of these different lines? So the question we're really asking, because we're holding pH constant, we're asking, what is my protonation state at this pH? So again, we've got 3 species. We've got NH4+, H2PO4-, and then CH3COOH, acetic acid. So as I draw my line across, I intersect first my NH4+ line at pretty much 0%. I come across here and I intersect at 50% on my brown line there. Red, I don't know if that's brown or red. And then I go all the way across here and then I intersect my green line at close to 100%. Okay, so that's the information we get from holding a horizontal line. Vertical line, right? We're going to hold now percent dissociation constant. And let's imagine we're drawing our line here at 50% dissociation. So the question we're asking when we look at this and when we intersect these lines is, what pH is required for me to be 50% deprotonated? And again, looking at where I intersect each of these graphs, I see it's about 9.3 for NH4+, 6.8 for H2PO4-, and 4.76 for my acetic acid. Well, what I'm really highlighting here, by choosing this specific pH and choosing this specific sort of deprotonation state, I've really identified the pKa's of these molecules. Actually, it was only the pKa for this guy. So if I'm at pH 6.8, 50% of my H2PO4- is deprotonated. By definition, that means I am at, my pH is equal to the pKa for that species. And if I set my deprotonation to be 50%, that means I will identify the pKa of those species. So the other important piece that we sort of talked about in this figure is to highlight here that these halfway values are really important. We're going to see lots of graphs where we're talking about halfway values. And here the halfway value is, by definition, the pKa. And so we have sort of another definition that we can think of for pKa. You can define pKa as the pH you need to be at in order for half of your molecules to be deprotonated. Okay, I'm going to say that again because it's really important. We can say that pKa is going to be the pH where you need to be at in order to have half of your molecules be deprotonated. So if we want half of our molecules to be deprotonated, we'd need to be at this pH for acetic acid. That's its pKa. We'd need to be at this pH for H2PO4-. That's its pKa. And we'd need to be at this pH for NH4+. That's its pKa. So a lot from a little figure, but it kind of introduces a lot of the concepts that we're going to use throughout this course. All right, so the last slide, again, a little bit of a dicey slide here. It was one that we sort of worked through in parts. You're going to see probably 1 to 2 slides like this per class, but they're intended to be things that are really concept maps that bring things together. When I have slides like this, if you guys find it helpful, I probably can make a little 10, 12-minute video that just kind of dissects that one slide to kind of like make sure it gets solidified. So we started out by writing this equation down here. This is a 2-part equation that has an enzyme and a pKa that you need to know. So the enzyme carbonic anhydrase is responsible for fixing water and carbon dioxide together to make carbonic acid. That itself is a weak acid with a pKa of 6.35 that will dissociate into H+ and HCO3-. This equilibrium in this system is one part of how your blood modulates its pH. We need to be able to think about equilibria really well. So again, thinking about equilibria, I use a push-pull analogy. So when you think about adding in something to an equilibrium, so any one of the reagents, either a product or a reactant, if we increase its concentration, the equilibrium will shift away from that. So a push-in of a reagent shifts away from it. If we pull a reagent out, meaning we decrease its concentration, we actually pull the equilibrium towards that. So I want you to think about push-pull as a way to thinking about how equilibria shift. All right, so why this is important, we're going to revisit this on Friday with our case study. We've got carbon dioxide kind of being a key player in this equilibrium. So again, thinking about increasing or decreasing concentrations of CO2 will shift this equilibrium such that we will increase or decrease the concentration of protons, and that ultimately is how we affect blood pH. So let's talk about 2 ways that we know right now that we can affect concentration of CO2. So coming back to our very first slide in our course, we talked about sort of this main fuel equation. We generate CO2 as a waste product. So CO2 as a waste product put into the blood will shift this equilibrium to the right. It will increase the concentration of H+, which means we drop pH, which means we go into a state of what we call metabolic acidosis. Acidosis, meaning we lower blood pH, we make it more acidic, and we call it metabolic acidosis because it's metabolism that's, initiating that process. Okay? Now let's think about another place that we can get CO2. Okay? Or again, it's the CO2 that's generated here as a waste that the purpose of breathing is to get rid of it. So let's talk about breathing here. The purpose of breathing is to take oxygen in. That's important because oxygen is really a nutrient, if you will, that we need to do cellular fuel metabolism. But breathing also exhales CO2, so it allows us to get rid of that CO2 waste product. So if we think about whether we're hypoventilating or hyperventilating, that affects what's happening with these. If you are breathing very shallowly, hypoventilation, in that case, you're going to have low levels of oxygen in your blood. And since we're decreasing the amount of CO2 that's going out, you're actually going to be increasing the concentration of CO2 in your blood. Increasing the concentration of CO2 in your blood means we push this equilibrium this way. We're going to increase H plus concentration, meaning we are going to create a state of respiratory acidosis. Replay that if you need to kind of go through that logic check. What's going to become important to our case study on Friday is talking about what happens when you hyperventilate. Now, hyperventilation means we're going to have excessive oxygen brought in, but excessive CO2 that's let out. So our CO2 levels are going to drop. They're going to go down. If we pull CO2 out of this equilibrium shifts to the left. That means we're also going to decrease H plus concentration. Decreasing H plus concentration means pH increases. If we increase pH, we put ourselves in an alkalotic state. So we would call hyperventilation that affects pH respiratory alkalosis. So ventilation is actually something that can affect pH either by increasing it or decreasing it. The metabolic situation here is really something that tends to create an acidotic state, at least from the situation that we're talking about. There's lots of aspects of metabolism that can do things to actually create an alkalotic state. But in our simple sort of scenario here, we're only kind of talking about metabolic acidosis. So I know that was a lot in those last two slides. Really hard to kind of try to do that if you weren't in class, which is why I wanted to remake this video here. But some of your homework questions you can do right now. Question number 2, you absolutely can do. That just has to do with picking a buffer. Remember, I said all you need to do to pick a buffer is pick a molecule, pick a weak acid whose pKa matches the pH that you want to be at. Homework question 3 and 4. There's some math stuff. I would wait until we kind of go through some of the buffer calculations in lab as kind of a review for how to do those problems, and then you're going to come back and you're going to feel much more comfortable doing these. All right, so that's a summary of what we covered in our crazy lecture today, but hopefully this is a nice resource for you to go back to, particularly with some of this early information.